Hi, I'm Fernando Pereira from UFMG, and today we shall talk about properties of type systems. We start with a property called progress. Together with another property called preservation, progress gives us something called soundness, or safety. Soundness means that a program will not reach a stuck state. That is, a state in which we must evaluate a term that cannot be evaluated. There is no rule to evaluate this stuck state. To prove soundness, we need preservation and we need progress. Progress says that a well-typed term is either a value or there is an evaluation rule to evaluate it so that it can take a step. To prove progress, we need a lemma called Canonical Forms. This lemma says something about the types of values. So if a value has type bool, then it must be either true or false. And if that value has type net, then it must be either 0 or the successor of a numeric value. To prove this lemma, we can simply inspect the typing rules. The inversion lemma already gives us the basic types of values. If you want, you can stop the video and take a look into the proof. Now let's see how we can state progress. It goes like this. If we have a term t, and this term is well typed, meaning that there exists big T such that big T is the type of t, then either t is a value or there exists another term, t prime, so that t evolves to t prime. We prove progress by doing induction on the derivation tree. So for instance, if we have this derivation tree in the figure, we can prove some facts for the root expression by assuming that these facts are true for the premises of the derivation. In the case of our programming language, we have 7 possible rules to consider. Any one of these rules could be the root of the derivation tree. So if we want to prove progress, we must reason about each one of these rules. So if the last rule is either t true, t false, or t zero, we are done because the terms referred in these rules must be values. Now let's assume we have an if-then else. We see that T1 is well typed. It has type bool. By induction, either T1 is a value or T1 can take a step. If T1 is a value, then either it's true or it's false. In the first case, we can take a step using if true. In the latter, we can use if false. If T1 is not a value, by induction, it can take a step. In this case, we use this fact as a premise to the rule if, and the whole term can take a step. Let's analyze more carefully the case for TSEC. What do we know if the last typing rule is TSEC? In this case, we know that the term is SEC T1 and that T1 is net. Now, if T1 is a value, then we are done, because SEC of a numeric value is also a value. If T1 is not a value, then it can take a step. That is, there exists a T1 prime such that T1 goes to T1 prime. In this case, we use rule eSEC to show that SEC T1 can take a step to SEC T1 prime. In the last typing rule in the derivation tree is tpred. Then we know that the term is pred T1 for some T1. Now we need to look into this term T1. If it is a value, then it must be either 0 or SEC of a numeric value, because T1 has type net. If T1 is 0, then epred 0 takes a step. If T1 is not 0, but it's a value, then epred SEC takes a step. Otherwise, T1 can take a step by induction. In this case, there exists some T1 prime, so that T1 evolves to T1 prime. And we can use this fact as the premise of rule epred to show that pred T1 takes a step. You can see this fact as a figure. This kinds of proofs are just a matter of plugging the right facts into the right places. If you want, you can stop the video and take a look into this figure to understand how it works. The case when the last typing role is T0 is similar. The proof is written in the figure and you can read it. There are three possible ways to evolve this term, and you need to show that at least one of them applies to evaluate a term like E0 T1. And this presentation concludes the discussion for progress. In the next class, we shall talk about the second part of soundness. This part is called preservation. Thank you.